Hi again. Last time we were able to find out the effect of elementary row operations as well as elementary column operations in the determinant of a matrix. We were also able to find out the conditions that make the determinant of a matrix 0. Today, we are going to study the properties of determinant. So the lesson objectives for today, you should be able to find the determinant of a matrix product and a scalar multiple of a matrix. Find the determinant of an inverse matrix and recognize equivalent conditions for a non-singular matrix, and also find the determinant of the transpose of a matrix. Beginning with matrix products and scalar multiples. So in example number 1, we're asked to find the determinant of a matrix product. We're given A and B, which are both 3 by 3 matrices. Find the determinant of A, find the determinant of B, and also find the determinant of the matrix product AB. Now we can use cofactor expansion method to find the determinant of A and B, and hence we will have here the determinant of A equivalent to -7, and the determinant of B, which is equivalent to 11. Now, to find the determinant of the product AB, we first need to find the matrix product AB, and the result is this. Now, we can now apply the cofactor expansion method to find the determinant of the matrix product AB, and the result is -77. Going back, we see that the determinant of A is equivalent to -7, and the determinant of B is equivalent to 11. So say we have the determinant of A times the determinant of matrix B will give us -77, whereas the determinant of the matrix product AB is also -77. Hence, in theorem 3.5, giving us the determinant of a matrix product. If A and B are square matrices of order n, then the determinant of the matrix product AB is just equivalent to the product of the determinants of A as well as B. In theorem 3.6, this gives us the determinant of a scalar multiple of a matrix. If A is a square matrix of order n and C is a scalar, then the determinant of the scalar matrix CA is equivalent to C raised to n, where n is the order of the matrix, times the determinant of A. In example 2, we're asked to find the determinant of a scalar multiple of a matrix. So we can see here that A is a 3 by 3 matrix whose entries are all multiples of 10. If we factor out 10, then the entries of matrix A becomes 1, -2, 4, 3, 0, 5, -2, -3, and 1. And consequently, we can find the determinant of A, which is equivalent to 5. By applying the theorem 3.6, which tells us that the determinant of CA is equivalent to C raised to n times the determinant of A. Now note that C is equivalent to 10 and n is equivalent to 3 since we have a 3 by 3 matrix, and the determinant of A is equivalent to 5. Hence, the determinant is equivalent to 5,000. Now, how do we find the determinant of the inverse of a matrix? In theorem 3.7, which gives the determinant of an invertible matrix, a square matrix A is invertible or non-singular if and only if the determinant of A is not equal to 0. In theorem 3.8, which gives the determinant of an inverse matrix, if A is an n by n invertible matrix, then the determinant of the inverse of A is simply 1 over the determinant of A. In example number 4, we're asked to find the determinant of an inverse of a matrix. So say A is a 3 by 3 matrix. So there are two ways on how we can find the determinant of the inverse of A. First is we can find the inverse of A using, say, Gauss-Jordan elimination, or we can use A times X is equivalent to I. Now, once we were able to find the inverse of A, we can simply take the cofactor expansion method to find the determinant of the inverse. Or what we can do is simply find the determinant of A, which happens to be 4, and apply the theorem which tells us that the determinant of an inverse is equivalent to 1 over the determinant of A. Hence, the determinant of the inverse of A is simply 1 all over 4. Now, here are equivalent conditions for a non-singular matrix. If A is an n by n matrix, then the statements below are equivalent. A is invertible. Ax equals B has a unique solution for every n by 1 column matrix B. Ax equal to 0. We have here the homogeneous system of linear equation has only the trivial solution. A is row equivalent to I sub n. A can be written as the product of elementary matrices, and the determinant of A is not equal to 0. Now, how do we find the determinant of the transpose of a matrix? If A is a square matrix, then the determinant of A is equivalent to the determinant of A transpose. This is theorem 3.9. In example number 6, we're asked to find the determinant of a transpose. So we have here A, which is a 3 by 3 matrix. Show that the determinant of A is just equivalent to the determinant of A transpose. So what we only need to do is to find the determinant of A first, and using cofactor expansion, we see that the determinant of A is negative 6. And we transpose A. That means we interchange the rows as with columns. So let's say all the rows of A become the columns of A transpose. And then we use the cofactor expansion method again to find the determinant of A transpose. And as you can see, the determinant of A transpose is also equivalent to negative 6. Okay, we were able to show the properties of the determinant, beginning with the determinant of a matrix product, then the determinant of a scalar multiple of a matrix, the determinant of an inverse of a matrix, and the determinant of the transpose of a matrix. In the next lesson, we are going to study the applications of determinants. We are going to find the adjoint of a matrix, as well as apply Cramer's rule, and apply the determinants in analytic geometry. So I'll see you then. Bye.